In this next video, we're going to explore what happens in the middle. So we've determined what happens as end behavior of polynomial functions, but now we want to look at what's going on in the center. And what's going on in the center is that your graph will have x-intercepts or zeros. So remember, these are called zeros because they're the things that make the y value equal to 0. So I could use substitution to determine whether an x value is a 0 by seeing if I plug it in for x. So for example, in this one, if I plug -1 in for x, does it make the value of the function, or the y value, equal to 0? So we could plug it in. Everywhere there's an x, I'm substituting in -1. And then I'm going to simplify. Now I would use a calculator, but I'm just going to use my mental math. So we get -2 minus 3 times 1 minus 1 plus 6. And then collecting like terms, I've got -5 minus 1 is -6 plus 6 is 0. So since the value of x at -1 gave me a function value or a y value of 0, then yes, -1 is a 0 of this function. So now what we want to do is, instead of just guessing random numbers and whether they're zeros or not, we want to look at finding zeros of factored polynomial functions. So for example, if you have a polynomial function defined as x squared times x minus 3 times 2x plus 1, we can let the y value equal 0 and determine the values of x that will make it true. So the values of x that will make it equal to 0. We do this this textbook likes to call it the principle of zero products, or Math 50 we call this the zero factor property. But what it is that whatever value makes each factor equal to 0 is going to make the whole thing equal to 0. So if we just take each factor and set it equal to 0 and solve, we can find the values of x that will make this polynomial function 0. So for this one, x squared equals 0. Well, if I take the square root of 0, it's still 0. This one I'm going to add 3 and get x equals 3. And for this one, I'm going to subtract 1 and then divide by 2. So this polynomial function would have 3 distinct zeros, one at -0.5, one at 0, and one at 3. All right, pause the video. See if you can figure out the zeros of this polynomial function. So I'm going to set it equal to 0. And then I'm going to set each factor equal to 0. It doesn't matter whether they're squared. We'll talk about what that means in a little bit. It'll determine the nature of that x-intercept. But really all it is that for these, every single factor gives you a 0. And then if there's more than one of that factor, it just, A, it makes the graph do something a little funky there, and B, it just makes sure that when you multiply them all out, you get the right number of x's to have that polynomial function. So for this one, I would just divide by 5 to get 0. This one I'm going to minus 1. This one I'm going to add 4, and this one I'm going to add 1 and divide by 3. So this one has 4 zeros, -1, 0, 1/3, and 4. It's really good to get in the habit of writing them in numerical order, just for some stuff that we're going to be doing later. One thing I wouldn't mind doing right here is just reviewing degree. So I want to look at, if we were going to graph these, which we're going to be, could you determine the degree of these polynomials? Because the more we see it, the easier it'll just be to kind of accept it. So for this one, we have an x squared times an x times another x. So if I were to multiply this all out, I would end up with an x to the 4. So this is a quartic function. And it would also be a quartic, or an even function, with a positive leading coefficient. For this one, I have x times x squared times x times x. So I have 1x times an x squared gives me an x cubed, times another x is an x to the 4, times another x would give me this an x to a 5. So this one is a quintic function. And this one would be an odd degree with a negative leading coefficient, whereas this one was an even degree with a positive leading coefficient. So don't forget, even though we're on a new topic, all that stuff still sticks. It will matter on the next lesson. Then you can give you a polynomial function that's not in factored form, and we can ask you to find the zeros. So at this point in the course, if I give you a polynomial function and I say to factor it, it means it's going to factor either by grouping or it's going to be a trinomial. So if I look at this one here, if I'm going to factor this, there's 4 terms. So I'm going to factor this one by grouping. So out of this first group, I'm going to take out an x squared and be left with x minus 2. Out of this group, I'm going to take the sign of the first term, and then I can take out a common 9. And I'm left with x minus 2. Because I have that common bracket, that is a greatest common factor of x minus 2. I'm left with x squared minus 9. And then this remaining bracket is a difference of squares that I could factor to x minus 3, x plus 3. So in 4.1, we will be making these harder that they do not factor. But in 4.1, every single polynomial they'll give you will be either a factoring by grouping or a trinomial. So now we could solve this by setting it equal to 0 and say that we would have 3 solutions. What makes x minus 2 equal to 0? What makes x minus 3 equal to 0? And what makes x plus 3 equal to 0? So for this one, my 3 zeros would be 2, 3, and negative 3. And if you just did that, I would give you full marks. You don't have to do the set notation. The set notation is just nice for getting you to practice writing zeros in numerical order and just declaring your solutions. All right, this one is a polynomial quadratic in form. So you can do a u substitution if you want. So you could do that this is a u squared, this is a u, and then substitute the x's back in. But I always just say, like, if you can see that this is a trinomial and it's going to factor two binomials multiplying together. And then because this is an x to the 4 in the beginning, we're just going to put an x squared at the front of each bracket. So x squared times x squared is x to the 4. And then we're looking for 2 numbers that multiply to give me negative 45 and add to give me 4. So you can go through the whole list. You can be like, oh, 3 and 15. Nope, that's not going to work. 5 and 9. Oh, there it is. So I can do minus 5 and positive 9. Now, you have 2 choices. You could try to do these in some sort of funky way, but I also can just set my brackets at any point in time equal to 0. So this one wasn't factorable past here, but because I now got it down to a quadratic, I could say, hey, I can still set each factor equal to 0 and solve. So x squared minus 5 equals 0, and x squared plus 9 equals 0. So for this one, I would add 5, and then I would take the square root, and don't forget, anytime you take a square root, it's plus or minus, and then this one as well. X squared equals negative 9, and then take the square root, plus or minus the square root of negative 9, and then we're going to simplify. So this is going to be plus or minus the square root of 9 times the square root of negative 1, which is going to be plus or minus, oh yeah, our textbook likes to write the I first. Oh no, we won't. Haha, because this one's a perfect square. So for this one, instead of writing I root something, I'm just going to put 3I. So this was a quartic function, and it had 4 x-intercepts that were all distinct. This one was a cubic function. It had 3 x-intercepts, but don't be stuck on that. This one was a quintic function, and it had 4 x-intercepts because one of your x-intercepts appeared more than once. Which leads us into a really great discussion on multiplicity. So when a factor, or a 0, appears once, we say that it has a multiplicity of 1. But when you have a factor appearing twice, so squared, it would have a multiplicity of 2. And when you have a factor cubed, we would say that it has a multiplicity of 3. Now for 4.1, that's all you need to know. So if you go down here, it'll say state the 0, or find the zeros and state the multiplicity. And so for this one, you'd have x minus 1 equals 0, x equals 1, the multiplicity is 3. You'd have x plus 2 equals 0, x equals negative 2, it would have a multiplicity of 1 because the exponent is 1. But we're going to continue this discussion a little bit just to give you a purpose for that and to set us up for 4.2. Is that these multiplicities will then tell us the nature of the graph around those x-intercepts. So if you have a multiplicity of 1, you're going to picture something like a y equals x function that has an exponent of 1. When you have an exponent of 1, no matter what the graph looks like, it will always just cross the x-axis at the x-intercept or at the 0. So we say the nature of the graph is to cross the x-axis if it has a multiplicity of 1. If it has a multiplicity of 2, we're going to picture our base graph of y equals x squared, where your graph comes in, touches the x-axis, and then comes back in the same direction. So I like to say that the nature of your graph is to touch the x-axis. A multiplicity of 3, we're going to picture a y equals x cubed, or a cubic function, which is a graph that starts down here, flattens out at the x-axis, and keeps going up. So I say that the nature of the graph is to flatten at the x-axis. Now, in general, every odd multiplicity, the graph will cross the x-axis. So this is just a plane crossing, and then a cubic would be like a flattening out and crossing. And then people always ask, well, then what would happen if you had a quintic? So what if you had a multiplicity of 5? Well, let's just take a quick look at Desmos. I'm going to hide that graph. It's coming up next. So if I did something like y equals x cubed, right? You get that flattening out. If I do any other odd exponent greater than 3, it also flattens out. So all of these flatten out just like a little bit more. The only one that just crosses is the multiplicity of 1. So a multiplicity of 1, the graph crosses. A multiplicity of 3, the graph flattens, but also crosses. Multiplicity of 4, it flattens, but also crosses. And so in general, if you're thinking about the nature of the graph, they just summarize it by saying that, oh, I just opened the same thing again. There we go. They just say that every odd multiplicity, the graph will cross the x-axis. We're just going to add to that and know that if it's an exponent of 3 or greater, that it also flattens at that x-intercept. And then if the exponent is even, so whether it's a 2, a 4, or 6, or so on, the graph will come and it'll touch the x-axis and then it'll go back in the same direction. So whether it's coming in from the top or whether it would be coming in from the bottom. And the textbook uses the language that the graph is tangent to, meaning it comes and it goes along and then it comes back up and it doesn't cross it. It just travels tangent to the x-axis. But I just shorten it and say it touches it. I'm like, ooh, touches it and then leaves again. So if we wanted to add to that, let's look at the nature of this graph. So this one we said that it had an x-intercept of 1, which would be a multiplicity of 3. And so we're expecting the graph to flatten a little bit, but still cross through the x-axis at 1. Oh, look at that. With this x-intercept, or this 0 of -2 has a multiplicity of 1, so we expect the graph to cross the x-axis. Ah, look at that. All right, let's try this guy. So with this guy, again, in 4.1, all you have to do is state the 0 and its multiplicity. For 4.2, you can start getting ready to talk about the nature of the graph. So for this one, we have an x-intercept of x squared equals 0, which if we take the square root of 0, we just get 0. But this 0 has a multiplicity of 2. If we were thinking about the nature of the graph around this x-intercept or this 0, we would say that it's going to touch or is tangent to the x-axis. For this one, we've got 2x minus 3 equals 0, so we would add 3 and divide by 2. Oh, that is opposite of what I just said. 3 divided by 2. If you're ever making those mistakes, show the work. Okay, so this is a 0 of 3 halves, and this one has a multiplicity of 1. If we were thinking about the nature of the graph, it would be crossing through the x-axis. And then the last one, we've got x plus 2 equals 0, x equals -2, and this is a multiplicity of 3, which means the graph is going to flatten. Now again, for 4.1, all you have to do is state the multiplicity, but the more you think about something and the more times you hear it, the more chance you are of remembering it, so it's going to flatten. So let's just check this on Desmos, and I already had this all prepped for us. So this is my equation here. And if we zoom in a little bit more, you'll see at the x-intercept of -2, the graph flattened. At the x-intercept of 0, the graph touched. And at the x-intercept of 3 halves, the graph crossed through the x-axis. So it's behaving as we expect it. And in 4.2, what we're going to do is put this all together. So end behavior combined with the nature of the graph around the x-intercepts will lead us to a sketch of every polynomial function. Are you excited?